Welcome to my talk. Thanks a lot for coming here. Thanks for organizers for organizing this. I know it takes a lot of time. This is my talk on how Python 3.11 is speeding up. And most of you might have already heard, but Python 3.11 actually came out on Tuesday this week. So it's really, really recent. So a little bit about me first. I'm a first year CS undergraduate student. And I'm also a serial procrastinator, and that's why I'm giving this talk, right? Because I should be studying for my finals, but I'm actually here. So and the thing is, right, I love Python so much that I volunteered to maintain Python's interpreter typing and typing module and the documentation. So I actually have commit rights to CPython, and I'm part of the core team for the language. So any opinions here again are not my own. They don't represent anyone else, my university, the people in Python, or my parents. So yeah, yeah. So anyways, what is CPython, right? So before there's a lot of terminology. So I'm going to start, right? Python, the language itself, is actually just a set of specifications. A lot of people argue with me about this, but just take my word, right? And there's actually multiple implementations of this. So you can actually implement Python, like the thing that runs Python is just a program. So you can implement Python in Python itself, you can implement it in Java, you can implement it in C#. So CPython is actually Python implemented in C. And there's a lot of alternative implementations like PyPy, Growl Python, Iron Python, Jython, Cinder, Piston, blah, blah, blah. So like, okay. So why am I even talking about performance improvements today? So CPython actually has seen stagnant performance for multiple versions. If you look at this news article by Phoronix, it's a Linux news website, there's actually almost no performance improvement from 3.8, 3.9, 3.10. And 3.11, so you see this huge jump, like it's like just there. So like, this is obviously something that it's interesting to talk about. And Python 3.11 is 25% faster than 3.10. And the range is actually 10 to 60% faster depending on your application. So, first of all, we need to ask ourselves, like, what metric? How are these numbers obtained? Like, am I just lying to you? And the answer is actually, we have this thing called PyPerformance. And it's just a benchmark suite that we actually run like toy benchmarks on. So we test like OOP, number crunching, calculating like, I don't know, distance from the sun or whatever. And then we just get the average of these. So this talk will actually follow roughly a document that I wrote on what's new for 3.11, faster CPython. And this will cover actually cheaper, lazy Python frames, faster Python function calls, and the specializing adaptive interpreter, which is actually what a lot of people are excited about because it's actually kind of like a mini JIT compiler. So the main problem here today is that Python is slow. And the things that make Python slow, right? Okay, wait, before I start, the asterisk there, right? Python is slow because, like, I think we all know that, but like, it's actually slower than PHP and JavaScript, which is quite surprising to a lot of people. Like, PHP is a lot faster than Python. So, Python is actually really slow for an interpreted language. So, things that make Python slow, right? You have dynamic attribute and method lookups, you have dynamic namespace lookups, and it's very object heavy, and I'll go more into this later. But it's box data types. So what that means, I'll also go again into later. And there's a lot of pointer chasing. So it means you need to chase down the addresses for all these objects. And in CPython, right, a list, right, is what you see on the left. And in NumPy or C, an array is what you see on the right. And if you have an array of floats, right, in CPython, it's actually an array of pointers, so an array of addresses to the float objects. So they're not even actual floats, they're abstractions over floats. Whereas, right, in NumPy or C, it's actually just an array of floats in C. So the benefit of having just an array of floats in C is two things. The first thing, you have something called cache locality. When things are packed very closely in memory, the CPU can actually read them faster because the CPU reads in a cache line. So it reads around 64 bytes at once. It doesn't read like 1 byte, 1 byte, 1 byte. It reads a whole 64 bytes, loads it into the cache. And then, right, when you read the next byte, it's actually free. It doesn't cost any cycles at all. So that's one thing. Cache locality actually speeds up the memory reads of this. So let's say you want to sum this, it's a lot faster on the NumPy or C array. And the second thing, right, is that because like these data types are not blocks, that means they're not structures. So we can actually make use of something called single instruction, multiple data instructions, so SIMD instructions. And that allows these things, right, to operate on multiple operands. Like, so you want to sum up, you operate on multiple operands at the same time. So it will just add multiple at the same time. Whereas for the CPython list, you actually add one by one and you have to call like the function that operates over these abstractions. So that's really slow. And many people are trying to fix that. So actually there's a team sponsored by Microsoft, and that's what's driving this main effort. There's a lot of people in the team, and there's also a lot of external contributors. And I just want to give some country stats because like this is really an international effort. There's people from the USA, the UK, Korea, India, and of course Singapore. So this is really an international effort. It's not just one like country trying to push Python forward. We're all trying to push Python forward. So subproblem 1, Python function calls are slow, right? And you have a Python versus a C function call, and a Python function call has to do a lot more work than a C function call. Python function call, namely, like the main overhead actually is it has to allocate a new Python frame object. And this is actually pretty heavy, and I'll go into it later. But in C function call, it's very simple. You just do a few like pointer increments, and then you just move pointers around, and then you just return the value, and then you just decrement the pointer. So like, I mean not decrement, minus the pointer. So like, this is like really fast in C, but it's really slow in Python. So we need to make it faster. So the first idea, right, is that we shouldn't allocate expensive Python frames. And this contributed by Mark Shannon. So in 3.10, right, a frame actually looks like this. And you don't have to read the code, but basically there's actually, the frame is a full Python object. And what Python objects means is there's reference counting information, there's garbage collection information, and also the frame needs to support stuff like tracing and debugging. Like it support traces in your code tools. So every time you call Python frame, you're actually paying a cost to support tracing. So like, why do you need this if you're not tracing? And in 3.11, there's actually two types of frames, and I like to call them debug frames and execution frames, which is a new lightweight structure. And there's a similar project by Instagram's fork of CPython called Cinder. A 3.11 debug frame looks like this. Okay, so it has all the tracing information again, and all the required execution information is in this single structure. And this single structure is just the bare information we need to execute a Python function. So it just has your globals, your names, your namespaces, your locals, so like and your built-ins. So this struct doesn't have any garbage collection or reference counting overhead at all. It's really, really fast. So I'm just going to show you how this looks like, right? So we're going to visualize the call stack. The red arrow is the instruction pointer, or just what the currently executed line is. So you call foo, it'll just put a frame onto the stack. Then when it's done, it'll just pop the frame off the stack. But here's a very interesting function. There's this introspect function, and it calls, okay, so it first pops a normal execution frame onto the stack. But it calls this very special function, sys.getFrame. Does anyone know what that function is? Has anyone even heard of that before? Okay, my friend has heard of it before, but he has played with Python more than I have, so I'm just gonna say no one knows about it. So, so sys.getFrame is a very special function, and it's actually what makes Python slow. In Python, right, you can actually introspect the current executing frame. That means, right, let's say you want to see, oh, who was my caller? You can actually say, oh, give me a current frame. I go and trace out the frame on the stack, and I find a caller. So you can actually find the callers like entire frame. That means you can access all the local variables, the global variables in the caller. And this is really slow because you can't do this in any other language, not even like JavaScript or anything. So this function, right, is a pain to support. But how we did it is we lazily create a debug frame on the spot, on the fly. So if you don't need it, it costs nothing. If you need it, it costs a little bit more, but not much. But otherwise, you're not paying for the cost of calling Python function anymore. You're not paying for the cost of supporting debuggers, supporting tracers anymore. That's how we made Python frames a lot faster and lightweight in 3.11. And one more thing is that the memory is actually reused. So don't read the slide because this is just a bunch of technical detail that I have to show someone else. But the long story short, right, is that every time you call a frame, right, we actually allocate a huge contiguous array, and it's all pre-allocated, like there's actually like extra padding at the back. So every time you call a new frame, we just add it to the back of the array. We don't actually allocate any new space. We're not calling malloc, we're not calling free. So it's actually 0 allocations. Every time we finish executing, we just take the frame off, but we keep the array there. So this giant array of space is being used. So yeah, and we already got rid of allocating expensive Python frame objects. So now the next thing is calling the evaluating function. So the second idea is to not call the evaluating function, and this contributed by Pablo and Mark. So the evaluating function in CPython, right, is actually just this giant switch case loop of all CPython operations. And previously, right, calling a Python function would eventually call this again. So Python function calls are actually recursive. So this is the call function operation in Python, and eventually it calls itself after many interactions. And in 3.11, right, here's how it looks. At the start, right, you have to handle methods. This is the actual code, by the way, from the source code of CPython. And it has to check that the callable as a Python function? If so, right, we create a new execution frame on the spot. Again, this is very lightweight, 0 allocations. Then we jump to the start of the same function again. So what that implies is simple Python function calls don't use C stack space. And you can actually, now Python 3.11 supports infinite recursion, but we don't advertise it because we don't want people to use it. If you increase the program recursion limit, Python function calls can actually recurse until your computer runs out of RAM. Like, this is something usually only found in functional programming languages, not in imperative programming languages. But it doesn't support all functions yet. Complex function calls do not work like this. But I'm trying to make that work in 3.12. So, second problem, right? Python operations are slow. So, right, there's a precursor to all this. So, a problem misconception is that Python is actually, it's actually an interpreted language, but it's actually compiled. And it's compiled with something called bytecode, which is an intermediary between the CPython virtual machine and the computer. So it's not assembly. And this is actually how it looks like. There's this module, right, called disassemble or this, and you can actually run this or this on a simple function. So the function is at the top left, and it says foo, then print a plus 1. So this is actually the actual operations that the CPython virtual machine operates on. And the first column, right, is the instruction offset from the start in bytes, the first red column. The second red column is the human readable operation code. And the last column is actually the operation argument. So in case you don't know how this works, it's okay. I'm gonna show you how it works in the next 1 minute. So right, okay, so the red arrow is the instruction pointer. So you have a resume instruction which is just nothing. You have a load global. So load global just loads now the stack first, and then it loads the print callable on the stack because we are trying to load print on the stack. Then it loads fast A. So okay, then we just load A, the A object. Then we say load cons 1 because we're going to add 1 to it. So okay, add load 1 onto the stack. Then we call binary op and addition. So we say okay, we pop the top 2 off the stack, add them together, and throw the result back onto the stack. And then precall does nothing. Call, right, will just pop the arguments off the stack, and it will pop the callable off the stack and the null as well. And then after that, it will push the result back on the stack. As you know, print doesn't return anything, it just returns none. So okay, we just push none back on the stack. Pop top, right, it's just because we're not using the none, we're not using the value from that operation. So we just pop it off the stack again, we don't need it. And then we load this constant none because all Python functions have to return none by convention. So we have to load none back on the stack, which seems a bit like redundant, but oh well. Then return value, which returns that none from this call frame. So CPython 3.10's implementation is simple to implement and reason about. But the thing is, right, the operators are generic and work for a wide range of objects, which is good for us because we don't need a lot of code. But it's bad for speed because generic operations mean there's a lot of overhead versus native C. So again, just to repeat previous slide, in Python, right, everything is dynamic and needs to be looked at runtime. And arithmetic operations are actually abstractions over objects or C structures. But in C, right, many symbols are resolved at compile time, not at runtime. And arithmetic operations are compiled to native machine code. So one observation that we had, or actually a lot of people have for the past 10 years, is that for dynamic language, some things are quite static. For certain operations, right, we know that they will always have the same type or have the same shape. So for example, this load global instruction will always be loading from the built-in namespace and not globals. And this binary op instruction is always going to be adding integers together and not in floats and integers. And this call instruction will always be calling the built-in C function print. It's not going to be calling a Python function, it's going to be calling a class. So, idea, specialized bytecode. That's what HEP 659, Specializing Adaptive Interpreter, is about. At runtime, we collect information about these patterns, and we actually override generic bytecode with specialized ones. So the specialized bytecode contains checks, right, to make sure that our assumptions hold true. And the specialized bytecode generally outperforms the generic bytecode by taking shortcuts. So the pipe is written by Mark with some inspiration from previous work by someone who wrote, I think, his PhD thesis, Stefan. So specialization looks like this. If you run the function a bunch of times and you disassemble it, it will churn out bytecode that looks different. And the bytecode, right, actually it doesn't look that much different, just the name looks like it just changed, yeah. Like that's what we did, how we made Python faster. Okay, no. But yeah, the names just changed, that's how we made, with longer names we made it faster, but no. Each of these bytecode takes shortcuts, and I will just show you a few examples. It's really cool. So loading globals is really slow, right? like imagine how you implement loading globals in Python. The first thing is you look in the global variable namespace. Then if you found, you return that. Otherwise, if it's not found, you look into the built-in namespace. Then if found there, then you return that. But if not found, okay, you raise a name error. The total cost of this worst case is 2 dictionary lookups. So like, what if we actually specialize for built-in lookups and module level lookups? And that's actually what we did. So load global built-in costs 0 dictionary lookups. It's actually only just a memory read into an array, which is as fast as you can get without a JIT compiler. And what it does, right, is it actually checks that the globals and built-in namespaces are actual dictionaries, and people didn't override them or shadow them. And we checked that the globals and built-in dictionary keys didn't change. This is really special. And then we retrieve the value by indexing directly into the built-in dictionary, and we make sure that it's present. So yeah, again, this is 0 lookup. So in Python 3.11, loading globals don't cost anything at all. They're almost free. They're almost as fast as loading a fast local variable. The second problem is that loading methods is pretty slow. And like you can imagine in most other languages, right, what you have to do is you have to work something in Python called a method resolution order. And this is just a tuple, right, of the methods, like the types that contains the method. So if you have a very complex inheritance pattern, Python will actually linearize it using an algorithm into just a very long array. And what Python does, right, is after it linearizes it, when you want to look up a method, it will look up that array or that tuple up. So that's called the method resolution order. And the second thing, after it looks through the entire array, is it has to look into the object's namespace. Because like, let's say you put an attribute there, you might have shadowed the method. So we need to make sure that it's not there. The total cost of this, again, is 2 dictionary lookups. Step 1, right, is actually big O1, not linear time. Because it doesn't have to actually traverse the whole tuple. What it does is it actually caches, Python really has hashed this in a hash table since 2.6 actually. But again, a hash table is still a hash table, it's still like kind of like a dictionary. Not really, people who know that, but not really. But again, just take my word for it. So this is really slow. In 3.11, right, method lookups don't cost anything at all. So that means if you look up a method enough times, it's essentially free. No matter how long the inheritance chain is, no matter how strange your inheritance pattern is, a method lookup is free in 3.11. And how we did this is that we ensured the MRO didn't change, the method resolution order didn't change first. We ensured the namespace key didn't change, so we make sure that something didn't just like shadow the method. And we obtain the cache method descriptor directly from the cache. So yeah, like this span out like method lookup by around 12 to 20%. It was pretty significant. So many other operations have been specialized, and actually I don't know how much time I have left. I actually hit a bunch of slides because otherwise like I'll go into them, but yeah, subscripts have been specialized. So if you subscript a list or tuple, right, or dictionary, we actually index directly the underlying object, the underlying data structure. Binary operations have been specialized too, but we didn't unbox them. So that means they're still operating on C structures. Loading attributes also has the same thing as loading methods, so we actually sped them out a lot. Most of attribute lookups are now 0 cost as well. Storing attribute also 0 cost. So we, yeah. So, and there's more interesting bits, right? And this is like the really geeky parts. So how are things even specialized? How do we decide to specialize something? We actually have 2 special instructions. One occurring at the top of the code object, and one occurring at the end of a for loop. And this actually increment a counter, then we just keep track of how often something is executed. After 8 executions, we determine that, okay, this code object is hot, so we will try to specialize it. And we swap out the generic instructions with adaptive instruction, and this adaptive instruction, right, is just a special instruction that will just gather data and decide, okay, which one I want to specialize into. So it will then rewrite itself to the final specialized instruction. So, right, at runtime, right, there are guards, right, that validate this. So, like, again, just now you saw there are many checks to make sure that all assumptions hold true. If they don't hold true, we just de-optimize back we fall back to the original instruction. If this happens enough time, right, we actually fall back to the adaptive instruction. So it will begin the cycle of collecting data again. Because if your code changed, then maybe the pattern and type change. So, okay, then we will try to find a new specialized instruction that will fit your code. So this actually works with Python's dynamism. And so CPython will actually change with your code. And Python will periodically attempt to be optimized, but this doesn't happen very often because specialization attempts, each adaptive instruction is 20 to 200% more expensive. It's really slow. So we don't do it too often, and we actually have something called exponential backoff. So every time we fail a specialization, we double the number of times it needs before we will try again to specialize for it. So this makes us not waste time on code that permanently can't specialize, because certain code is just way too dynamic. And where's all this data stored, right? We actually have this fake instruction. If you run a disassemble instruction and show caches, right, passing this argument show caches equals true, you can actually see there's actually fake cache instructions that lie right after your instructions, your operations. And this instruction actually maps directly to a C structure. So accessing these objects are extremely fast. Just increment the instruction pointer, cast to a C structure, access the variables directly. So yeah, like on most platforms, this is quite fast. And I want to give a shout out to a package. There's actually this package by one of my colleagues, Brent Booker. He created this tool that allows you to see which part of your code is specialized properly. So like the green parts, I mean that the Python actually managed to specialize it fully. Red part means not so much. Yellow is like, I mean red part is bad, like so we didn't specialize it at all, and yellow is like, okay, a mixed bag. And one more thing before I end off, right? So we actually have this lazy dictionary optimization to save space also in Python 3.11. And this optimization, right, is pretty simple. What happens is, basically for an object, you have a namespace, right, so to store all your attributes. The thing is, this is actually a full-blown dictionary, but again, we don't need a full-blown dictionary because the dictionary contains garbage collection overhead and some other pointers because, like, in case a user needs to use it, right? So we don't need that. We just store it directly inside the object itself, and we just get rid of the header. So that saves some memory, and we only lazily create them again when a user requests for it. So there's too many things to talk about and too little time, but there's actually also zero cost exceptions. That means back then, right, when you do try except in Python, just entering the try block itself costs some time. Now, if it doesn't raise an exception, exceptions are zero cost. So try except is zero cost, provided you don't raise an exception. If you raise an exception, it's actually a lot slower. We also make exceptions cheaper, so we make them consume less memory. And there's also regex speedup in the regex module. So the key takeaways is that making CPython faster while maintaining networks compatibility is really hard, but actually it's not impossible. And code that doesn't use Python's dynamic features or dig into our internals are actually implicitly rewarded with better performance. If you want faster code in 3.11, don't like do all these weird things. Yeah, I'm sure actually like the second, third, and fourth one, okay, third one maybe you all heard before, but second and fourth one, no one has heard before. Okay, so, yeah, and last thing is try out CPython 3.11. We are really happy with it. What's in our future, right? So 3.12 will be even faster. Again, I'm not part of the faster CPython team at Microsoft, but here's what I know, right? The work in progress roadmap, and again, tentative, is 3.11, we have the specializing adaptive interpreter. 3.12, we have a short tracing interpreter. So we'll actually combine these special instructions into a long trace, and we do guard elimination. So that means we will remove duplicated guards and make them super fast. And then, right, 3.13, right, we have a simple JIT compiler, maybe, because that might come in 3.14 instead. We're not too sure. 3.15, I don't know, because that's like when I graduate uni. So yeah, I don't care. So, so yeah, that's the end of it. My email, right, is kenjin@python.org. If you have any questions or you want to reach out, just email me. Yeah, that's all. So yeah, thank you. Yeah.
Sorry, let me pass you the mic.
Hello. Yeah, thanks for saying Python is a specification. Yeah. But if it is like that, then how can it be slow, right? What you're meaning is CPython is slow, not Python is slow.
Yeah. You're right. The thing is, right, when I gave this talk, right, I was like, wait, do we even know what CPython is? So I was like, okay, wait, I better just put Python. Otherwise, they think it's like something else. So yes, you're right. CPython is slow. The Python implementation is just specification is just a specification.
Any other questions? Okay.
Yes, hi. Yeah, thank you for your talk. Really insightful on the internals of CPython. It's really amazing. Wanted to ask, how did you guys decide on the number 8 for when to decide to optimize for the adaptive interpreter?
Okay, so that's a very good question. The first thing is, right, most of the time, we just choose a number. Okay, so we didn't want a number too high because we don't want it to like try too many times, as in wait too long before specializing. But the number, right, most of the time it's arbitrary. The second thing is that we just decided that it fits well into an integer, because I mean right. So yeah, actually in 3.12 we are thinking of making it 4. So I actually don't know how the number came about. Yeah,
Oh,
I think
see.
it just fits well into like an integer. So
Yeah, I was thinking whether you guys actually did like benchmarks based on like maybe like 2, 4, 8 or something.
Oh,
but yeah.
I don't think so.
Okay.
Yeah,
All right, thank you.
no problem.
Any other questions? Wow. Sure. Let me come to you.
Okay, dumb question. So how long did you work with Python before they gave you a Python email? Very important question, you know.
Okay, right. So once you get commit rights to Python, right, you're given you can request for an email.
Cough, cough, how do you get commit right?
Uh,
Who do you bribe? I also want to bribe someone to get a
Yeah.
Python email.
yeah. So my story is a bit long. So like
You have time,
no. So what happened was I was like bored at home. Then I decided to contribute to CPython, because you know that's what procrastinators do, right? They contribute to open source. Then then I was mentored by some people. Like they saw that my work was, I mean, like they thought I was quite enthusiastic, so they just mentored me. Then after like 1 year of like contributing patches to Python, they thought, okay, you're like ready for this, so they just put me up for a vote. Then there's like a vote where everyone will just vote whether you should be promoted or not. Then they promote you. Yeah.
There's a council.
Yes.
Yo, there's a council who like looked at you and was like, okay, you are ready.
Yes,
So
yes.
you're now a Python developer.
Yeah, something like that.
Cool, cool. I'm gonna hand back the mic to the actual. Like, yeah.
Oh no.
Yeah, this is more of like a general like soft question. But basically, like you said, like for instance, like PyPy is like faster than CPython, right? Is there like some reason why CPython cannot like say implement certain ideas that PyPy does?
Okay. So okay. So PyPy, right? The main reason why we didn't just use PyPy, right, is because PyPy has some backwards incompatibility with some C packages. So the thing is, right, they actually have done a lot of work to improve it. So actually the situation is a lot better than it used to be. But the thing is, right, even if like 1% of C packages don't work, we cannot use PyPy. And that's basically like why they're actually going along with their own plan instead of just using PyPy. As to whether we're importing ideas, right, I think most of the time we actually have already been taking ideas from PyPy. I don't mean stealing them, I just mean like we're like sharing ideas. So like, for example, right, some of the faster interpreter stuff, right, is actually like, okay, some of the 3.7 stuff, so not the stuff now, was actually taken from PyPy. But the jig compiler stuff, right, I'm not too sure about that, because again, it's very up in the air, and that's like 3 years from now, 2 years from now. Yeah, but PyPy has also taken stuff from us. Like, I'm not sure if you know, but in 3.11 there's like better tracebacks, like better, so more informative tracebacks. And PyPy implemented that also from like after seeing, actually with help from one of the core developers in CPython. Yeah.
Okay, wow. So, any other questions? Come.
Okay. Yeah, so you mentioned about like the unintended bonus side effect
Yes.
of not using the C stack trace
Yes.
finally.
Yes.
So one of the main limitations of Python is that it uses so much C stack trace until you have a seg fault, because when you try to do a lot of recursion.
Yeah, correct.
So so in functional programming, right, we have this concept of tail call optimization, right?
Are you gonna ask if that's going to be implemented?
Yes.
No. The creator of Python actually addressed this before, but because tail call optimizations will cut out traceback information, he didn't want it. Yes, unfortunately, but because now all the Python function calls, not C calls, but Python function calls use the heap. You can write your recursion and it's a lot faster. In fact, a recursive Fibonacci function in Python is 1.7 times faster in 3.11 than 3.10. Yeah, so just increase the recursion limit and write all your recursive functions that you want. Yeah.
Okay.
Yeah. But I thought he had a question before.
Oh, hello. Sorry, I have a dumb question. So, just now I saw that if the specialization for function fails, it will be exponentially incremented. So does that mean that you're encouraged to write smaller functions now instead of like huge functions? Because if it's a huge function, it would be a lot more dynamic. If it's a small function, then it'll be more defined input and output wise. So if you write smaller functions, then the specialization should, in theory, go through more, and your code will go faster.
Okay, so there's two parts to that question. So the first thing I want to say is that if you have a function that's too big, like it's over a certain size, we're not specialized because like specialization takes more memory. So we don't want to like make Python take a lot of memory. But that limit is really large, so I don't think you should ever hit that. The second thing is how well your function specialized doesn't depend on the size. It actually depends on how well typed the functions are. So we actually found some through our own experiments. If you use MyPy or static typing, right, most likely your functions will specialize well because you're already like conforming yourself, you're fixing yourself to a set of specifications. So we will probably specialize well for those cases. Yeah, I think he had a question.
Hello. I think mostly you're talking about single-threaded performance.
Yeah.
Are there things looking at multi-core, for example, multiple threads?
Yeah, okay, so this is really cool. 3.12, right, we're going to add, if nothing goes wrong. So we're going to add sub-interpreters. So we're going to allow you to run an interpreter inside interpreter, and we're going to have something like ghost channels, and we can actually pass primitive objects around. So that will allow you to scale things better than the current way. But if you're talking about removing a GIL, then that isn't works yet. Yeah.
Okay. So, any more questions? Actually, I have one.
Okay.
Oh,
wait,
you?
Yeah, one question.
No.
Yes, one question.
Yeah.
Yeah.
Come.
You want to go for PyCon?
Wait, where,
Yeah,
which
yeah.
one?
This year lah. Next year.
Wait, you mean in Singapore?
Yeah, Singapore.
Wait, when is it? Later, like later my exam.
June
is like-
holidays. June holidays. Yeah,
Okay.
holidays. Yeah.
Sure. I mean,
Go.
Oh, okay. Okay. The thing is, I might be working at the time, so I'm not too sure. But like I'll see when you all have more concrete plans near the time. Yeah.
Okay. Actually, I have one question. So, I mean, I guess like what advice you would give for people who wants to do something like as cool as what you're doing, right? I mean, like a lot of us are procrastinator, but I don't see most of us will start think about, oh, I want to contribute to open source, right? So, any advice for everyone who is interested? Yeah.
I don't think I'm a good person to give life advice because I honestly have I'm just a uni student with weird priorities in life. So like the thing is, you really have to do a project that you use yourself because otherwise you won't be interested in like continuing on. You'll just like feel okay, I'm tired of this, and you just give up. So like if you use the project that you're contributing to, you'll feel more motivated. But the funny thing is, I don't even use Python that much now. I just write mostly in C because of what they make me do. So yeah.
Okay, so the answer is to have weird priorities, right?
Sure.